Okay, I'm on the Many Collisions tab now, and as we go through these tabs, it adds a little bit more complexity, but then also I think a little bit more reality as we get to reactions. Most of the experiments that you'll be doing will be in this rate experiment tab, so I at least wanted to walk through this Many Collisions tab. So let's see, what do we notice? We still have similar type reaction, an A reacting with a B and C. We've got the ability to raise and lower temperature. We've got this reaction coordinate. But a couple new things here in that instead of just a little pinball, we've got like a bicycle pump or like a gas pump where we can deliver lots of molecules. And then we've got some new options here for recording what's happening. And one of the things I'm going to turn on is what's called the strip chart. So what this will do is monitor the amounts of atoms or molecules over the course of time. So let's do this. So what I'm going to do is just grab the pump, and notice I've got some A. So I'm going to pump in some A molecules. Okay. And then what the software does is it keeps track of how many are in there. So there's 9. And if you go up here, you can see that it's plotting 9. Okay, so now what I'm going to do is add some of the other reactants, so this BC. So I'll pump some of those in. And so I've got, 6 of those added. So as we watch this, this goes back to probably some of the gas law things that you would have been exposed to, and maybe something like Chem 1, where these things move around. They're not all at the same rate. But as I look at this, I see molecules bumping into one another, and I see not a lot of reactions. But one of the things that you might spot is, like, notice right here, here's one of these little gray balls. So that means that a reaction must have happened. And then if I look over here, so an A and a B, somewhere I say, oh, right there, there's an A and a B. So if I look over here at the current amounts, notice that one of those A's, I was at 9, reacted. Now this is a little bit different than what we were observing back in that single collision. In the single collision, we only had one set of molecules we're looking at. And notice that we're always plotting the average energy. But it turns out that some of these things gain speed, or they gain energy. And it turned out that even though the average energy was lower than the activation energy, there was a reaction that occurred. So that's really a reality type of thing that happens with reactions. So if I do raise the temperature though and get the average energy over that activation energy, I should see lots and lots of reactions. So let's just see what happens here. So I'm raising the energy. Now as I'm raising the energy, I might find that some of these things do react. I haven't observed that because the concentrations of these haven't changed. These numbers haven't changed. I'm going to raise it, raise it. Ooh, see, I saw a little bit of a bump there. So there was a little bit of reaction. So if I raise it up above that activation energy, well, then I see bigger changes happening. So there was a bigger change there as far as what was happening for the reactant. And if I look over here now, I've got a total of 3 of those things. So we're dealing with some kind of small numbers here, so it's somewhat hard to get a real accurate depiction of what's happening. But it does give us a really good model of I think a real chemical reaction. Okay, so I'm going to stop this, and one of the things I'll show you is a little bit more concentrated solution. So I'm going to I can hit pause down here at any time, and I can play it again or pause. But I'm just going to reset these. Reset all. Now I like to use that strip chart. There's some other charts here, but I kind of like the strip chart. And what I'm going to do is just put in like 100, and then 100. And this is the type of scenario at least I begin to picture as far as lots of atoms and molecules in a solution. Notice on this strip chart I can kind of zoom out and see what's happening here. So notice that there's reaction happening here. Now notice that A and B, the A and then the BC molecule, I've got a lot more of those because those are on the lower energy side of this reaction coordinate. So this should come to some sort of equilibrium, and that kind of is plateauing out, where I've got more on this side, and then I've got not as many on this side because this is the lower energy. Now the thing to spot here as far as this activation energy, I'm going to hit pause, is that when I ran this reaction, it took so long for this to reach that equilibrium. So even though the average energy was below, some of them in here gain enough energy to react. And because there's so many around here, they eventually do react and reach what's called a steady state, whereas at about 80 of this system and about 20 of this system. Okay, so now what I'm going to do here is now change the temperature. So I'm going to reset this. I'm going to go back to where my temperature is like above that activation energy. I'm going to put in 100. Oh, I want to make sure I got that strip chart on, and I want to put in 100 of these and hit return. And notice what happened here, in that the time it took for these things to react and to get to probably some sort of steady state was much quicker. It was much quicker. So this change was very quick. Okay. All right, so then I'll stop that. Okay, so that was kind of the highlights with the many collisions. You can get more atoms and molecules. Notice that you get more reactions over that single collision because these obtain the right geometries and they obtain the right energies. The energy that has to, some of them have to get over this bump. Okay, so I'll stop this video and then I'll make one more that'll help explain some of the things I want to do in your actual experiments.